I'm sorry for the delay in the session. So our first speaker is Suvendu. Suvendu, are you there?
Yeah, I'm here.
Can you share your slides, please?
Yeah.
Sorry for the delay. I was in some other meeting.
Actually, your voice is too loud here, so probably some disturbance are there. So
yeah, I will just yeah. So Suvendu will tell us about supermassive black holes in the universe. Please carry on, Suvendu.
So, good afternoon, everyone. So, first of all, I would like to thank the SOC for inviting me to give this talk. And of course, I am happy to be here in person because I could meet many new faces and also interact with most of them. And also refreshing my memories of old ASI in 2016. Okay, so the title of my talk is Supermassive Black Holes in the Universe. So this image, I think everybody is familiar with this image. This is M87, of course, everybody knows. So M87 as imaged by Event Horizon Telescope. So now, thanks to this observation, we know that M87 has a black hole, a supermassive black hole at the center of 6.5 billion solar mass. So that's huge. Now, the black holes are of different masses. You know the stellar mass black holes, and then there are intermediate mass black holes, and there are huge supermassive black holes. So if you look at the space density of supermassive black hole in the universe, you will find it to be 0.5 million solar mass per unit megaparsec cube. And we know the galaxies are megaparsec apart. So this means that every massive galaxy would have a supermassive black hole at the center. So, and thanks to the Hubble Space Telescope, and we now know that whether it is an elliptical galaxy or it's a spiral galaxy, every massive galaxy hosts a supermassive black hole at the center. Okay, these are just two examples of HST images, just for representation. Now, these black holes which are sitting at the center, they influence their host galaxy or vice versa. So they grow or evolve together. And this is clear from this plot here. So on the left, you see the black hole mass as a function of bulge luminosity. And on the right, you have the black hole mass as a function of stellar velocity dispersion. So this correlation is valid for, let's say, 5 order of magnitude in black hole mass, and it's very, very strong. It's true for classical bulge as well as the elliptical bulge, elliptical galaxy. So now this much stronger is the correlation between this black hole mass and stellar velocity dispersion, which is on the right panel. So now these masses are measured dynamically, and because they are normal galaxies, we can easily resolve them, and they're very local in the local universe. So here, just in comparison, so you see the normal galaxies M33 and M100. These names looks like Samsung Galaxy mobile phones, but it's like M33 and M100, just for an example. And so in case of normal galaxy, you could see clearly the host. But in the case of AGNs, the core is much, much brighter, as you know, that it outshines the host galaxy. And even if you go further at high redshift, it will be much more unresolved. So you need a high spatial resolution to resolve it, right? So how do we measure the masses of these black holes in the AGNs? So there are actually many methods to do this. So let's say galaxies are mostly classified in normal and active galaxies. So in the case of normal galaxies, you could use the stellar and gas dynamics. So one of the examples is shown here. Let's say you see the orbit of stars in our galactic center, which is Sagittarius A. So this is actually remarkable because this discovery gave the Nobel Prize in 2020. Like everybody knows about this picture also. So if you map the orbit of the stars over time, and then you can infer the invisible object that is sitting at the center, along which all the stars are orbiting, right? So this, but for the case of AGN, the type 2 AGN, you can use the megamasers, or you can use the reverberation mapping technique. And based on this primary method of black hole mass estimates, every time you want to make it a simplified relation, right? So that you can use it for a large sample. So we arrived on different fundamental empirical relations, which is black hole mass and stellar velocity dispersion that I showed earlier on slide. And this is true for AGN also. In the case of AGN, you also have a M-sigma relation. And then based on the this empirical relation, we have also secondary mass estimates. So you can use this O3 line width, which seems to be strongly correlated with the stellar velocity dispersion. So if you use O3 line width, you can estimate the black hole mass also. And also you can, from the reverberation mapping, we arrived at a strong correlation between the size of the broadline region and the luminosity of the AGN. So, so, and the application to these mass measurement methods are, you can use it for, let's say, low redshift AGNs, high redshift AGN, BLAC, and APSRQs are also there. So, what is this reverberation mapping that we are using for, let's say, AGNs at redshift 0.1 to, let's say, redshift objects at Z equal to 7. So, this is a simple method. So, for example, you have a black hole and which is surrounded by an accretion disk. So, any fluctuation that happens here, it will propagate in all directions, right? And a part of this fluctuation will arrive to a distance observer. But some part of this light will be absorbed by the clouds which are sitting in the broad emission line region, and they will absorb it and re-emit, but after certain time delay, because this light has to go there. So this delay is corresponds to the light travel time from the disk to the broadline region. So if you do the monitoring of the continuum emissions, and as well as if you do spectroscopic monitoring, and then you just can estimate the lag because you do the cross correlation. So you can get the time delay, the difference between time. And since you are doing the spectroscopy, you have the spectrum from which you can calculate the FWHM or line width. And then you can use this simple relation M proportional to F, RBLR, sigma square, and G. So almost all things are known here, except this factor F. So now the problem is that how we measure the F factor, because it depends on individual objects, their geometry and their kinematics. Okay. So currently we use a average value of F factor. So this average is 5.5 based on the M-sigma relation of normal galaxies and AGN. So we just match them and arrived at 5.5. Because this needs actually a huge amount of work to model the kinematics and geometry, which you cannot do now in most of the cases. So the most remarkable achievements of this reverberation mapping method is to arrive at a strong correlation between the size of the broadline region and the luminosity of the continuum at 5,100 Angstrom. And this relation is remarkably strong. You see the scatter is only 0.13 dex. Dex is in log scatter. So, and this plot is from Benj et al. 2013. And the slope is 0.5, and this is this agrees with the photoionization calculation as well as the inner ring of dust sublimation radius. So this was a picture in 2013. Okay, and now the picture become very ugly. It's completely messy because we have a many different kind of objects, right? So here some of the objects we are strongly deviating from the size luminosity relation. These objects are actually strong AP2 emitting AGNs. They are narrow length supernovae galaxies. And so these, thanks to these guys, Du et al. 2018 and 2016, they made these things messy. But then they solved it also. Okay. So what they did, so if we want to use this relation to all AGNs, we need a proper calibrated relation, size luminosity relation. So they found that this relation is not only depends on the BLR size and the luminosity, but it also depends on AP2 strength of the iron emission lines. And now, if you consider this, so now instead of continuum luminosity, you just also used AP2 strength. So now again the scatter reduced to 0.196, so it's much lower. So what we actually trying to do is to calibrate this size luminosity relation, including more objects which are at the high luminosity end of this diagram, as well as using some other kind of objects like strong radio louds, AGNs, to check that if this relation is valid for all type of AGNs or not, or should we include some other factor like the AP2 strength. Well, so we have been monitoring around 70 high luminous AGNs, and here is one of the example from one 2019 paper. So we have been using this MDM 1.3 meter telescope, MDM 2.4 meter, LOAO and DAO for photometry monitoring. And we are using the spectroscopic monitoring. For that, we are using LEAK 3 meter telescope and MDM 2.4 meter. So most of them are in the US. Okay, so here what you see that continuum varies a lot. It also make a V type of pattern. And the spectroscopic continuum also follow the same thing, and there is no lag because both of them are continuum. However, if you see the emission lines, this H beta and H gamma, it also follows the continuum, but there is a lag between these two. So this arrives a little bit late compared to this one. And this delay or lag you can calculate just simply doing the cross correlation. Okay, and this turns out to be 43 days. So since you have the lag, you can also estimate the mass because you can construct the mean and RMS spectrum, and you can calculate the FWHM and these things. So we got the mass of these objects is 3.6 into 10 to the 7 solar mass. Now, initially I said the gas motion are realized, and we use this simple relation m proportional to v square r, right, to estimate the black hole masses. But can we verify that? So to verify that, of course, you have to plot v square along y-axis and r along x-axis. So, and if they follow -1 relation slope, then you can say, okay, this what we assume is actually correct. So here we found that the slope for this is -1.21 plus minus 0.28, which shows that the gas motion is realized. Now the thing is that here we have included a few more objects. Some of the objects are here. Low luminous objects are here compared to other high luminous objects that in our sample we have. So there will be some here in populated. And we also included a few radio loud objects. This is one PKS15. Another object is PKS0736. We see that these objects 0736 is remarkably following the size luminosity relation of the standard size luminosity relation, and it's not deviating. So you can check the poster outside by Sivangi. So the thing is that all the relations that I talked about, it's that based on H beta, because on the x-axis you see the H beta. Okay, so but H beta is limited to redshift 0.8. So what about high redshift? If you want to go redshift 4 or 5 or 6 or 7, so there you have other emission lines, mostly the MG2 and C4. I mean, they are still there, but they are redshifted out of the spectral coverage of ground-based survey. Okay, so you need to have MG2 and C4, but can we use those lines and how good are they? So let's find out. So to do so, we actually created a catalog of quasar spectral properties, and this catalog contains 0.5 million quasars. So it's available online, so everybody can play with it. What we plotted here and showing here is the line FWHM along y-axis as a function of redshift. Okay, and similarly we have the FWHM as a function of polarimetric luminosity along in this plot. And in each plot, what you see is the density contours at different levels. So we have 3 sigma, the outer contour, and if you go then 2 sigma, 1 sigma, and then 40% density contours. And also you have the mean of this distribution, so at each redshift beam. So the plot actually is showing that you have almost no or very weak evolution of line FWHM as a function of redshift, because you see it's almost straight line. So whether you can consider H beta emission line, MG2 emission line, or C4 emission line, you see the same across the all redshift. And look at the redshift range, now it's going from 0 to 4.5. Here also, we found a very weak correlation with the FWHM and the continuum luminosity. So, but if you plot the luminosity as a function of redshift for all these 0.5 million quasars, you see a strong evolution. Okay, you see that as you go higher redshift, the luminosity is increasing. One reason is that this is a flux limited sample, so you cannot detect the low luminous objects at high redshift because your telescope is not sensitive enough, right? Same. So there are actually observational bias for this particular purpose, low luminescent for at high redshift. But we eventually see that there is a strong evolution that we found for these flux emitters also. Now, if we calculate the black hole mass based on, let's say, mg2 emission line and as a function of h-beta emission line, so we found that all those objects, their mg2 masses are correlated with the h-beta masses. And if you here is the histogram, the distribution between this mg2 mass divided by h-beta. So we found that the mean of this is almost 0.01, so there is no offset kind of, and the dispersion is 0.3 days. However, if you compare the C4 emission lines as a function of mg2, so which is here, you see that the distribution is very wider. So that means it's much more scattered. And also there are systematic deviations of 0.209. So this suggests that we need to do further calibration for the C4 masses. But because we know that C4 have a non-gravitational wind component, so which affects the black hole mass measurements. But this suggests that we actually need, and anybody can work on that, the black hole mass estimates based on the C4 to find a better correlation. Okay, so whatever we have, we can do a plot of black hole mass and see its evolution across the redshift up to z equal to 5, right? So here we plotted the black hole mass as a function of redshift for redshift less than 0.8.
Hi, my screen has frozen. Hello? Hello? Is there a problem? Hello?
Yeah, Mousumi, I cannot hear or see anything.
Yeah, it seems like it was disconnected for a moment.
Oh, okay.
Yeah. We're trying to connect it.
Okay.
Yes, so
Yeah, carry on, Suvendu.
yeah, so what I was telling is that if you see the distribution, the upper envelopes, which is this one, it flattens up to redshift z equal to 2, and then it reduces if you go lower redshift. So which means that massive supermassive black holes who are no longer signing at the optical quasar at low redshift. The most interesting part is this one. So you see the black hole mass, it flattens out, of course, and there are no mass, no black holes with mass greater than 20 billion solar mass across all redshifts. So if you go anywhere, you see that there are no black holes with a mass of 20 billion solar mass in the universe. Okay. So is there any observational bias again here? So look at this photoionization simulation using cloudy code. So this actually predicts that here is a line equivalent width in the unit of Armstrong, and here along x-axis we have the black hole masses. Okay, for different emission lines. So what this plot shows actually, it shows that if the black hole mass is beyond, let's say, 10 to the power 8 or so, the line strength or equivalent width decreases. So that means if you go for a heavier black hole mass, line strength is so small that you cannot detect using the existing telescope. Okay, so if this is true, then we could expect that more hypermassive black holes in the universe. But then again, how do you explain that how they form? Because if you want to form a hypermassive black hole at high redshift, then the black hole has to grow up to that redshift, right? From a small black hole to large black hole. So here, this plot actually showing all the known.
Hello? Has it hung again? Hello, Nayana, can you hear me?
Yes, Mousumi, it is hung again.
Oh, okay. This is really bad. First I am late, now it's hung. Okay. Wait, I'll call Ruby. Hello. Has it? Okay, I think it's hung again, everyone. So we'll just wait a few minutes until it comes back. So this is very unfortunate. Okay. Okay, it's come back now, I think.
Yeah, somehow we keep on disconnecting. So
Yeah, yeah, we're a little running late also because of me. And so I'm really feeling bad. So Suvendu, can you finish up a little soon if you don't mind, 5 or 7 minutes?
I'll be very quick. I think I will take 7 minutes now.
Okay, okay, continue. Yeah, thanks. Now maybe another 5 minutes, Suvendu.
Okay, sure.
Okay.
So what this plot is showing that if you plot all the hypermassive or high-level redshift objects, z greater than 7, they are here. In this plot, what is showing that their black hole mass is along y-axis. X-axis you have redshift, but it's going from redshift 30, that is mean early universe, toward the present universe. Okay, present will be somewhere here. I cannot move my mouse here, but anyway, somewhere here probably. Anyway, so what we see is that if you want to grow these black holes with the Eddington accretion, then you need a seed black hole which is around 10 to the power 4 to 10 to the power 5 solar mass. That means you initially need this much of heavy black hole to make it bigger until this much. So which is very much challenging because we know that early universe the black holes are formed, let's say heavier black holes are formed by population 3 stars, which are mostly the hypothetical stars. But even this cannot explain. The dense star cluster even cannot explain. So you have to have the direct collapse black hole scenario to explain this heavy seed. So if you find more hypermassive black holes at higher redshift, this means that you have more challenges to make a theory of this. Okay, model. Here I plotted how the Eddington ratio as a function of black hole mass looks like. So here you see the Eddington ratio of these objects and the black hole mass along this axis. So we see that there is an inverse correlation, and where the accretion rate decreases. So here is accretion is low. I mean here is high. Accretion rate is decreases as you go to the hypermassive black holes. Okay, so that's mean high accreting hypermassive black holes are rare in the universe. So that's mean we are not finding the black holes which are high accreting, but they are hypermassive also. And we found that the low mass black holes are heavily accreting. That we know that narrow line superton type AGNs, which are accreting higher rate. And the average Eddington ratio for these SDSS quasars lies between 0.1 to 0.01 to 1, with an average of 0.1. Okay, so since I will be finishing soon, so just to talk about, so this diagram I already showed, where the strong F2 emitting AGNs are deviating from this relation. So they are actually, if you plot this again, the F2 strain as a black hole mass and the F2 strain as the Eddington ratio, these sources show some a particular distinct separation between these two. So narrow lines and broad lines. So NLS ones are twice F2 stronger than the BLS ones, and the NLS ones are low massive black holes, hosting low massive black holes than the biggest ones. But this one reason for this is that these objects are actually, by definition, they should have a smaller FWHM, smaller mass, because they have a smaller FWHM. Because though if you plot with respect to all quasars with a point less than 0.8, you see narrow line separations are located here in this part of this. So their FWHM is much lower. So if FWHM is much lower, then you will see a much higher, much lower black hole mass also. Okay, so we see that evolutionary scenarios where the merger produces, let's say, narrow line separation galaxies, which will eventually grow at broad line separations. Then again, the quasars, and when the quasar is dead, we live with only the elliptical galaxies, let's say. So finally, I come to the conclusion. So as I said, that reverberation mapping scaling relation is very useful tool to estimate the black hole mass throughout the universe. But we need to properly calibrate those relations to use it for all the AGN populations. And we found that there are no black hole mass with mass heavier than 20 billion solar mass, and high accreting objects are low massive compared to high mass black holes. And now the field will be going in new directions once we have the SDSS 5, which is the black hole mapper project program, and the JWST, which was launched a few months back. That will find more high Z AGNs or black holes. So at last, I would like to advertise one JRF position that I already advertised. So the deadline is approaching 31st March. If you are MSc backgrounds or BTech backgrounds, you can join us to this journey. So with this, I thank you to all for your attention.
Thank you, Suvendu, for a very comprehensive overview of the black hole mass determination and their growth. So we have time for a few quick questions. Can I ask the organizers present there to take the questions from the public sitting there?
So just the previous slide where you showed that the evolution, can you just explain it a little bit in details, whether you were talking about the with the redshift or the same object
will evolve with time.
But we see the supermassive black hole mass differences too, right? Whether NLS S1.
So NLS ones will accrete further with time, and it will grow to a PLS ones. Okay, and because we know that broad lines has a higher massive, so narrow lines ones will grow to the broad lines separate ones, and then it will become quasars, because NLS ones are just a low luminous separate one galaxy.
Mass also.
Yes.
Okay.
So this is just to put in the context that based on the accretion rate, what we can say here. Okay.
Yeah, because in high, whatever AGNs are detected in high resolution, most of them are quasars, right?
Yes, quasars.
And we are detecting separates in the local.
Yeah, we are only detecting now. So these are separate galaxies, because we cannot detect, let's say, observationally cannot get low luminous AGNs in the high redshift. You cannot find them.
So your point is that
you have to grow that to the AGN or quasar phase, because you have to go on the process, right?
So you mean that it's just a sensitivity or our observational deficiency that we are not looking at, but there are a much more number.
Yeah, redshift. If you see the redshift and luminosity plot that I said, that the observational bias are there. It's called null and twist bias. Yeah. So there you will have much more low redshift. Low luminous, high redshift object. This should be there.
Okay. Any other questions? Anyone else? I can't.
Question.
Yeah.
Not relation. So you were saying that So for these sources, it was like the scatter was reduced by putting the iron strength in there.
Yeah.
So the next plot that you showed, the one where the scatter was reduced. So this 2 et al. 2018.
Before, just I have to go there. Where is that? Probably. Okay, but you go
Yeah,
with
so
that
what,
question.
yeah, so this one, no, the bottom one.
Yeah.
So did they put this iron strength for all the sources or only for super intense sources in this plot?
So if you put all the sources, if the source iron strength is weak, then you do not see any difference, right?
It will not matter much.
So iron strength is, if it is large, then only it will make difference.
Yeah.
So they actually did this good spectral decomposition for all the objects, and they find out this equation based on the iron estimates of all the sources. So they did actually all the sources.
Okay. The other thing is that in the lower luminosity regime, so there are few sources which this DLR size estimates, right?
Yes, yes.
So, are there any works going on which are, people who are doing these kind of studies for low luminosity agents?
Yeah, so low luminosity agents, they are actually, as you know, that they will be less variable. Okay, so they may not vary at all. So the people what they do, if I am doing a program, so I would like the object to be variable so that I can get some results. After 6 months, if I don't get any results, then that doesn't make sense. So low luminous objects are less variable. These objects are particularly different one because they are high variable separates, but there are not many. So one is NGC 4395, which is a dwarf galaxy hosting in the galaxy. So they have very low mass black hole. So it's 10 to the power 5 or something like that. So that objects people do monitoring of.
So this 4395, it fits into this relation, right? Or? It's
little bit difficult because there are not exact estimation of the broadline size. Some people used C4 space telescope, some people used Gemini, and we actually did one Cake and Gemini we used, and we monitored, but we arrived some kind of size which is putting here.
Okay.
There are two problems in this because it's difficult to estimate the luminosity of the continuum also because the host galaxy is so diffuse that you cannot estimate properly the luminosity. So based on that, also there is a different problem, but only there.
I think we have to move on to the next talk because we're a little short of time. So Suvendu, thank you for your talk, and maybe everyone can put the questions in chat. Suvendu,
yeah,
maybe you can answer it in chat. Thank you.
Yeah, I will have, and you can mail me also if there is any discussion. Anybody can mail me.
Yes, that would be great. Yeah. So Nayana, are you online?
Yes.
Yes, thank you. Can you please share your slides? Thank you. So Nayana is now going to speak about her low frequency radio studies of a fast blue optical transient. Nayana, please go ahead.
Yeah. So am I audible and clear?
Yes, you're audible. Yes.
Okay. Hi, I am Nayana. I am the DST Inspire faculty at Indian Institute of Astrophysics. Today, I will talk about the low frequency radio emission from a very interesting astronomical transient called AT 2018 COW, or we call it AT 2018 COW. So the COW belongs to a very new class of astronomical transients called fast blue optical transients, or FBOTs. So these class is characterized by its very fast evolutionary timescales. They appear in the sky and reach to its peak luminosity in a few days. Also, it declines in a couple of days. So only very high cadence wide field surveys can detect these events, and these are discovered only a few years back. Since then, these surveys are populating this phase space of fast transients. They are also characterized by very high optical luminosities and blue colors. So the challenge is the fast time scales and high peak luminosities together. These are difficult to incorporate in traditional supernova models. So there are various attempts in the literature regarding the progenitor models of FBOTs. It includes tidal disruption events, merger of white dwarfs, shock breakout from dense circumstellar shell, etc. However, so far there is no conclusive evidence for or support for one particular scenario for different FBOTs. Now, coming to the radio emission from these events, radio emission from FBOTs, it's understood to be due to the interaction of the shock from the explosion with the circumstellar medium, so which is created by the stellar wind of the progenitor system. So the left panel shows a cartoon diagram of the shock interaction with the CSF. So the explosion throws the stellar ejecta at high velocities to the CSM, which creates a shock. At the shock, particles are accelerated to relativistic velocities, which could emit synchrotron radiation that can be probed at radio wavelengths. Now the CSM is created by the stellar winds, which are order of magnitudes slower compared to the shock velocities. Hence, this interaction and the follow-up of these radio emission essentially gives information about a longer mass loss period in the history of the later phases of stellar evolution. Now, in addition to the emission processes, there could also be several absorption processes like free absorption or synchrotron self-absorption. And as a result of the combined emission and absorption processes, the radio light curves or spectra will be like bell-shaped as shown in the right panel. There is a optically thick phase and there is a smooth transition to optically thin phase. So the idea of radio observations and modeling of these transients is to follow these events from days to years post explosion and get the temporal and spectral evolution of these radio flux densities. And there are analytical functional forms developed long back since 1982 to model these observations and get physical parameters of the system. Now coming to the physical parameters that can be constrained from radio observations. Here I show in the right panel is a self-absorbed synchrotron spectrum where I have marked the peak of this spectrum that characterize the peak frequency and peak flux of this spectrum. Now, in the optically thin phase, the functional dependence of the flux density, it depends on various parameters. The interesting parameters are R and B, where R is the size of the emitting region, which is essentially the shock radius, and B is the magnetic field, and D is basically the distance to the event. In the optically thin phase, the functional dependence is different, but again, it depends on R and B. Now, at the turnover, basically, we can invert these two equations to obtain R and B. So, it will be something like this. Let's not worry about all the other parameters in the equation. The observational values which we need to obtain are Fp and mu p, which are peak flux density of the SSA spectrum and peak frequency, which is basically the turnover frequency. And D, we know F is a volume filling factor, which we need to assume something. So basically from these two observables, we can estimate the size of the shock and magnetic field. We can also get a rough estimate of the mass loss rate by assuming a magnetic field scaling relation. So in a very simplistic scenario, we assume that a fraction epsilon b of the shock energy density is fed to magnetic fields. Now the rho CSM in the shock energy density is basically created due to the mass loss rate, mass loss from the progenitor, hence rho can be represented in terms of m dot. So these are the physical parameters of the system or the environment of an explosion that we can constrain from radio observations. However, there are only a handful of F-bots which has shown radio emission, and I'll be talking about the first and the most detailed studied F-bot of this sample, 2018 cow. So this event happened in a dwarf galaxy at a distance of only 60 megaparsec. So at the time of discovery, this was the first F-bot to be discovered in local universe. It happened in 2018 June. So there are a lot of observational features which were surprise and intriguing about 2018 cow. So first thing is the rapid rise. It rose to peak luminosity in the optical bands in less than 3 days. And it has showed remarkably high optical luminosity. And the optical spectrum was initially featureless for up to 10 days and later followed by short-lived broad emission features. And it has also shown very luminous X-ray and radio emission. Now I'm focusing more towards the radio emission studies on this object. So there were a couple of groups who did early high frequency radio observations. By high frequency, I mean that mostly observations above 5 gigahertz up to few hundreds of gigahertz. So these observations gave clue about the immediate environment, the immediate radius, the immediate mass loss, the density of the immediate environment of this event. However, the role of UGMRT is unique because the low frequency observations will always probe the extended environment. So I can explain that with this figure. So the figure shows spectra of any transient like supernovae or F-bot. And different colors represent different epochs. Now, as you can see, as time passes from day 47 to day 943, the turnover is cascading to lower frequencies. So now, so at early times, high frequency radio observations can constrain NUP. However, at later times, we really need to go to sub-gigahertz frequencies to constrain NUP and hence the shock radii and densities. So this is the strength of UGMRT bands where we can really do long-term follow-up of these events, which other high-frequency observations cannot do. So keeping this in mind, we set our goals. So to be particular, the high-frequency observations which are there in the literature, the follow-up happened till day 92 after the event, and they basically probed a radius up to 7 times 10 power 15 centimeter around the explosion. And from their synchrotron spectrum, the mass loss rate was derived as 4 times 10 power minus 4 solar mass per year. So this period or this observational epochs correspond to a time 2 years prior event. So this mass loss rate is the mass loss rate of the progenitor system roughly 2 years before the explosion has happened. So we aim to explore the properties of the environment beyond the radius of 7 times 10 power 16 centimeter, and we aim to look at the mass loss rate of this progenitor system at an earlier phase of evolution, much before 2 years. So we followed this event with the UGMRT during 11 to 570 days post-event. Left panel shows the UGMRT light curves at 3 different frequencies, and right panel shows the spectral evolution. And these are the first sub-gigahertz light curves of an F-bot, and probably the only well-sampled sub-gigahertz light curve of any F-bot. So we went ahead and modeled these observations. So I did not show you the actual analytical formulation, but the gist of it is the following. These models basically take care of the emission, radio emission from synchrotron theory. And each model, I have shown 4 different models, which are basically assuming that for example, FFA model assumes that FFA is the dominant absorption process along with the synchrotron radio emission. SSA again is assumes SSA as the dominant. Now we also have tried to incorporate inhomogeneous FFA and SSA models, which essentially says that the dominant absorption process is FFA or SSA, where the emission structure also is inhomogeneous. So we found the best representation of the data is by inhomogeneous SSA model with the best reduced chi-square. Now from the best fit model, we differentiated the best fit model to get the peak frequency and flux density and the time at which these light curves peak. Now to remind you for once.
Nayana, can you finish in another 2-3 minutes?
Sure, yes. So as I mentioned previously, we are interested in getting FP and μP from observations and estimating shock radii, magnetic field, and mass loss rate. So we went ahead and calculated the shock radius at these three different epochs, and we found that the shock radius is expanding as expected from an explosion with a nearly constant velocity. And we also estimated the magnetic field strength. So the shock radii estimates are consistent with VLBI measurement. So VLBI essentially tries to measure the size of the emission by very long baseline interferometry, by high resolution imaging basically. Now we also estimated the mass loss rate with the UGMRT observations and shock parameters, which are of the order of 10 power minus 6 solar mass per year. Now these mass loss rates correspond to an epoch of stellar evolution about 19 to 46 years before the event, before the actual explosion. It is interesting to note that these numbers are roughly 100 times lower compared to the estimates which are already there in the literature from high frequency data, which corresponds to a few years prior explosion. So we could interpret this result as that the progenitor has gone through an enhanced phase of mass loss close to the explosion, which is like 100 times more, which can essentially create a dense bubble around the immediate vicinity with a sharp density cut. So this is the main conclusion from our study. So I will leave you with the summary. Thank you.
Okay, thank you very much. Thanks. So are there some questions? I'm not seeing any in the chat yet. Okay, maybe while people are getting their questions, Nayana, I can ask you. I know that this is a transient. How does it compare with these, very spectacular fast radio bursts that we see about in the literature a lot nowadays?
So these are quite different from FRBs. FRBs are just flashes, and they also have, first of all, I don't know much about FRBs, but these F-boats can be more compared to very energetic supernovae or superluminous supernovae explosions, not really to FRBs.
Okay, thank you. So is there anyone in the hall?
Hello. Yeah, Nayana, this is Anirban here.
Hi, Anirban.
So you said that the rise time for these kind of objects is less,
Yes.
right? So you need the exotic thing like merger of two white dwarfs or something like that to explain the to be the progenitors for these kind of objects.
Yes.
So can it be like explained in a normal nickel powered scenario where you have a asymmetric ejecta where in the line of sight your ejecta mass is lesser, so you have the rise time lesser, something like less than 5 days or so. Can this be possible?
So if that is the case, we can certainly explain the short rise time, but then the problem is, how do you explain this high peak luminosity?
Oh, I see.
Yeah, and also in the case of white dwarfs, the another problem is after day 12, we do see some hydrogen and helium features, right, which are less likely in the case of a white dwarf.
Okay. So are there any questions?
Hi, Anna. Harsh here. So I have a question about this TD scenario that you talked about, like this one of the progenitor model from the for these F-boats. So I remember that for the cow, people are puzzling about whether it could be a intermediate mass black hole about 10 to the power 4 or 5 solar mass, or it has to be more. So is there any constraint that can be put up from the radio observation on the same thing?
Not really from radio observations, but regarding the TDE scenario, there are also some arguments against it, saying that this event is 1.7 kpc away from the nucleus of the galaxy. So the position of this event is not really in support of a TDE scenario.
Okay. I remember like there were a case discussing about intermediate mass black hole, which can also be in the like globular cluster kind of thing.
Okay.
So like I think that's one of the probable scenarios. It should not directly rule out on just on the basis of like this distance.
Yes, I agree that it is proposed as one of the probable scenario. But from radio observations, we really cannot constrain.
Okay.
Okay, so I think now we have to move on to the next speaker. If you have more questions, maybe you can mail Nayana. Silpa, are you there?
Hello everyone, I am Shilpa Sasikumar. I am a final year PhD student at NCRA GIFR and I work with Professor Preeti Kharb at NCRA. So today I will be discussing the results from our work on a radio polarimetric study of radioquiet AGN. A vast majority of the Asian population launch weak radio outflows such as jets that typically extend to a few tens of kiloparsec scales or outflows that are often diffuse or wind-like. These are the radioquiet AGN. On the other hand, only 10 to 15% of the Asian population launch powerful jets that extend to several hundreds of kiloparsec or megaparsec scales, and these are the radio loud AGN. This is the radio loud radioquiet dichotomy, which has been quantified by means of the radio loudness parameter R given by Kellerman et al. 1989, which is the ratio of 5 GHz flux density to optical V-band flux density. According to this definition, radio quiet AGN has an R value less than 10 and radio loud AGN has an R value greater than equal to 10. There is yet another class of AGN with intermediate radio loudness values, and these are the radio intermediate AGN. These sources are known to be the relativistically boosted counterparts of radio quiet AGN. Key questions. There is a general consensus about the origin of radio emission in radio loud AGN, which is the Blanford and Sarnak mechanism. In this mechanism, the relativistic jets are produced by the electromagnetic extraction of rotational energy from spinning black holes. However, the origin of radio emission in radio quiet and radio intermediate AGN is poorly understood. For instance, we do not know if the emission mechanism is that of the Blanford and Sarnak or Blanford and Payne or even a combination of both. In the Blanford and Payne mechanism, both energy and angular momentum are magnetically extracted from the accretion disk to power AGN winds. Also, why radio outflows in radio quiet and radio intermediate AGN are stunted or small scaled is another open question. Possible origins of radio emission in radio quiet AGN, as proposed in the literature, include low power jets, winds, star formation, and coronal emission. Recent studies, including ours, have shown that radio polarimetric observations in conjunction with spatially resolved emission line observations have provided insights into these fundamental questions about the nature of radio outflows in AGN. So this is the first source I'll be discussing in today's talk. It is 3 Zwicky 2, which is a radio intermediate quasar and also the first Seyfert galaxy where a superluminal radio jet was discovered. Here we present the upgraded GMRT 685 MHz contours of the source, where a triple radio structure comprising of a hotspot, core, and hotspot is clearly detected. We also detect a misaligned lobe to the south in the UGMRT image, which was not detected in the higher resolution VLA observations. The red ticks here present electric polarization vectors whose length are proportional to fractional polarization, and fractional polarization is the ratio of polarized intensity to total intensity. So the regions where you find longer ticks are the ones with high fractional polarization, whereas the regions with shorter ticks are less polarized regions. Also, the orientation of these vectors is determined by the polarization angle. For optically thin regions like the jets and lobes, inferred magnetic fields will be perpendicular to these polarization vectors, whereas for optically thick regions like the core, inferred magnetic fields will be parallel to these polarization vectors. Therefore, in this UGMRT image, we find that the inferred magnetic fields are transverse to the jet direction all the way from the core to the southwestern lobe. And in the southwestern lobe, the inferred magnetic fields are aligned with the lobe edges. These transverse magnetic fields could be interpreted as a series of transverse shocks that order and amplify magnetic field by compression, or could also represent the toroidal component of a large-scale helical magnetic field associated with the jet. I would also like to mention that we have developed a polarization pipeline that can reduce both the continuum and polarimetric UGMRT band 4 GWB data, and this pipeline is available public at this location. In this inset on the right, we present VLA 5 GHz image of the southwestern jet lobe region of the source, and here again the vectors are fractional polarization. In the smallest inset, which is the zoom in of the core region, the vectors are polarized intensity. In the southwestern lobe of the VLA image, we again find that the inferred magnetic fields are aligned with the lobe edges, suggesting shock compression. In the core, which is optically thick, the inferred magnetic fields will be parallel to these polarization vectors, hence transverse to the local jet direction as well as the VLBA jet direction, which is in the direction of my cursor. We also find an optically thin jet component J1 close to the core, where the inferred magnetic fields will be perpendicular to these polarization vectors, hence parallel to the local jet direction. The parallel magnetic fields could be interpreted as a poloidal component of the helical jet field. This is one possible explanation. There is also an alternate explanation to our polarization findings, which is the following. Recent works by Miller et al. 2012 and Mahidipur and Constantine 2019 have shown that toroidal magnetic fields can efficiently thread MHD winds and poloidal magnetic fields can thread AGN jets. So if this is the case, one cannot rule out the possibility of these transverse magnetic fields, the UGMRT image, being the toroidal fields threading an AGN wind that has been sampled on larger spatial scales than sampled by the VLA observations. And when we say wind, it could either be an accretion disk wind or the outer layers of a widened jet like a jet sheath, or even a combination of both. And in keeping with this model, the parallel fields in the VLA image could represent the poloidal fields threading the spine of the jet. Thus, overall, we find that radio polarimetry has been able to probe different layers of outflow with characteristic magnetic field geometry like the jet spine versus jet sheath / wind that are sampled on different spatial scales. This is another source marker in 231, which is known to be transitioning from the radio quiet to radio loud state. And here we present the historical VLA images of the source at 1.4 GHz on the left and 4.9 GHz on the right. In both these panels, the green contours and red ticks correspond to around 10 arcsecond scale images, whereas the blue contours and black ticks correspond to higher resolution, that is around 1 to 4 arcsecond scale images. In both these panels, the ticks represent magnetic field vectors, which have been obtained by rotating the polarization vectors by 90 degrees, assuming optically thin emission. The lower resolution images detect a diffuse lobe-like emission to the south that extends to around 55 kpc, whereas the higher resolution images detect a poorly collimated jet that extends to about 25 to 30 kpc to the south. Coming to polarization, we detect a region close to the core in the higher resolution images where the inferred magnetic fields are parallel to the jet direction. This is a zoom in of the core region to show the parallel fields. Whereas in the lower resolution images, we find series of transverse magnetic fields all the way from the core to the edge of the southern lobe. So this is similar to what we saw in 3Zwiki2, that is poloidal fields threading the spine of the jet sampled in higher resolution images and toroidal fields threading the AGN wind sampled in lower resolution images. Thus, overall, we find a composite jet plus wind radio outflow in these sources where the jet threading poloidal fields is immersed inside a broader magnetized wind threading toroidal B fields. And we have tried to propose a model that shows a possible connection between the different spectral states of the accretion disk and the multi-component outflow in AGN. And the model is the following. We suggest that the winds are launched from the outer regions of the accretion disk, which are in soft state, characterized by Shakur and Sunya 1973 model. The jets are launched from the inner regions of the accretion disk, which is in hard state and characterized by the advection-dominated accretion flow. So such a coaxial outflow would appear co-spatial in projection like what we see in our sources. Next, in order to bring in the local host environmental effects into the picture, we have also carried out a study comprising of VLA 5 GHz radio polarization in conjunction with O3 emission line data for a sample of 5 type 2 radioquote quasars selected from the Quasar Feedback Survey with Chris Harrison as the PI. Now, these 5 sources are known to exhibit prominent kiloparsec scale radio structures like jets, lobes, and bubbles. These sources are also known to show a close association between the radio structures and ionized gas morphology and kinematics. Therefore, these sources are ideal candidates to study the interaction between radio outflows and the ambient medium. Out of the 5 sources, we detect polarization in 4 sources, and here we present images of 3 of these sources. As already mentioned, these sources are known to show a spatial correlation between the radio emission and O3 emission. We find an anti-correlation between various polarized knots and O3 emission in the sources. Essentially, we find polarization in the jet lobe regions which have a dearth of O3 emission and a lack of polarization or an absence of polarization in regions dominated by O3 emission. Such an anti-correlation has been previously observed in some of the radio loud AGN in the literature. And it is explained as a result of the depolarization of radio emission by emission line gas. And this can happen in 2 ways. One, where you have an irregular Faraday screen of emission line gas which is clumpy on scales smaller than the observing beam. So the screen of emission line gas will depolarize the radio emission from the lobes, and this is the external depolarization effect. Second one is the internal depolarization effect, where the entrained emission line gas inside the lobes of the sources mix with the synchrotron plasma and depolarize the lobe emission. By modeling the external and internal depolarization effects using the relations given in Byrne 1966, we can come up with some interesting numbers. So we have carried out this analysis for one of the sources, that is J0945 plus 1737. Here we have modeled the external depolarization effect, which enabled us to estimate the size of the emission line gas clouds. And the typical scale size ranges between 10 to the power minus 5 to a few thousands of parsec for the source. For comparison, this number turns out to be in the range of 10 to the power minus 5 to a few hundreds of parsec for radio loud AGN. By modeling the internal depolarization effect, we have been able to estimate the amount of thermal material mixed with the synchrotron plasma of the lobe of the source. And that turns out to be about 10 to the power 6 solar masses for the source. Similar studies have not been extensively carried out for radio quiet AGN and especially for the sample. However, we do have estimates of the ionized gas masses for some of the Seaford galaxies from optical imaging and spectroscopic studies. And there, this number turns out to be in the range of 10 to the power 5 to 10 to the power 7 solar masses, and we find that our result is consistent with the literature. For comparison, the radio loud AGN show ionized gas masses of the order of 10 to the power 9 to 10 to the power 10 solar masses, and this difference is reflective of the large differences in the lobe sizes between radio loud and radio quiet AGN. Also, the anti-correlation between polarization and O3 emission could be interpreted as a signature of the radio gas interaction or a possible AGN feedback in these sources. So I'll leave you with a summary, but I would just like to highlight one point, which is the following. Overall, our results suggest that a close interplay between the various emission components and the surrounding environment is likely to be responsible for the stunted form of radio outflows in radio quiet and radio intermediate AGN. Thank you.